you have got this delta naught propagated back via output side weight W, and then you take f dash of net at the hidden layer, reshape it, and then you calculate the hidden layer delta. Using hidden layer delta, your input side weight matrix, that is the hidden side weight matrix, you are updating. The whole step I just put it inside for 1000 steps. That is a stochastic gradient descent process. This is the updated W, and with the updated V, I supply the testing. Testing is just one feed forward flow with the updated W and V. I present all 4 records. I just pass on to one feed forward flow. What is the hidden layer output? Adding the bias, and then you calculate the output side net and output side prediction for the 4 records. For the 4 records, look at the probability score I have got. It is not satisfactory. What I'm supposed to get? We are supposed to get first record should be close to 0, and the last record also 0. The second and the third record should be class label is 1. That means the update is not sufficient. Okay, the update is not sufficient. Maybe even though with the 1000 iteration, if the update is not sufficient, means the learning rate was very slow. So to speed up the learning from 0.01, okay, let me make it as a 0.2, little bit to speed up. It's the same 1000 epoch. Let me check the probability score now. Some marginal improvement, right? At least the first record and fourth record, the probability score gone down below 50%. Earlier it was above 50%. A marginal improvement. So the two things I do simultaneously, we have to speed up the process once again from 0.2 to 0.3, and also the iteration also from 1000 times to 5000 times. Let me update. It's a very good sign. Can you see there is a big difference that happened? Now the probability score from 49% it reduced to 13%, approaching 0. And this guy also from 49% it reduced to approaching 0%. At the same time, the second and third record is approaching towards 1. Earlier it was around 0.5 something. Now it is 79–80%. That means the algorithm is converging in the right direction. Okay, but still it required more steps to reach the destination. So what I do, I just double the update from 5000 times to 10,000 times. I update it. Again, the process taking place very slow, which indicates that I need a slightly large step size. Okay, from 0.3 to 0.4, I redo this. Very big difference, right? 0.06, 0.06, 94%. Little bit, if I increase the iterations from 10,000 to 12,000, let us see it's marginally improving or not. Okay, this one 94% to 95%. A little bit fine tune this learning rate from 0.4 to 0.45, and this guy I make it from 12,000 to 15,000. Because as you are nearing the destination, you should not overshoot it. So I'm taking a very small step size. That means a very fine tune I'm doing it. I'm not doing a very coarse tuning. So this looks better. 0.036, 0.036. 96.5, 96.5. So almost it converged. So when compared to the initial level, this is far better. The successfully it differentiate the first record and fourth record from the second and third record. So earlier it was not linearly separable. Now it is separable. Because using the lab one notebook using a single layer perceptron, even though we increase the number of updates to 1 lakh, 2 lakh, 10 lakh, even infinity, your error got stuck at 50%. There's no improvement that happened. Okay, little marginal update we'll do whether to see whether further maybe 97 or 98% I'm able to get or not. Let me check. 20,000 epoch. It's overshooting. So this is what it's overshoot. It crossed the global minimum. Okay, which is equivalent to increasing the learning rate. So the optimal value I was getting, okay, which was 96% or 96.5%. So that is the optimal value. If you keep increasing it, what you are means you are crossing the global minima. You are rising to the ascending direction. You're reaching here, you're trying to go. So to visualize this idea to the context of regressor, assume this is something like your data points and you are trying to fit a best fit line. Assume initially you started with some random position like this, then you're adjusting like this. Then after 1000 epoch, you adjusted like this is the best fit line. And if you keep on doing it, maybe you are moving away from this. You'll be moving in the opposite direction. So that is what the reduction in the probability score which indicates. So it have to stop at which point it gets saturated. Even though if you keep increasing the iteration, the value gets settled somewhere at 0.96, 0.965. So that is the safest point, and that's the saturation point. You should stop it. Okay, around close to 97%. It's reasonably good. 97% and 3% roughly, not bad. So now we try to visualize this. I wanted to visualize this using a 3D graph. So why 3D graph? Because we have 3 neurons, right? First we presented the first input, x1 and x2. 0, 0 I supplied. It is being mapped on H1, H2, H3. On the trained weight matrix, I'm going to record this. Okay, of course, here we kept this as V and here we kept as W. With the trained V matrix, I'm just trying to map 0, 0 to H1, H2, H3. Then I present 0, 1, I map down to H1, H2, H3. Then 1, 0, map. Finally, 1, 1, you map. Now, for the 4 records, now I have the representation H1, H2, H3 representation, isn't it? Now I'm going to take this H1, H2, and H3 representation in a 3-dimensional visualization. I want to see how the data points appears in the transformed domain. So I can consider this hidden layer as a transformed domain. At the same time, I'm going to visualize my X1, X2 data points. We are going to visualize in the original feature space. In the original feature space, already we know in the original feature space, these guys are linearly non-separable. Of course, with the 2 features in 2-dimensional view, you can visualize. But after transforming this to the hidden layer with the trained weights, we are going to visualize how these 4 data points appears. So for that, what you need to do, we have to present all 4 records. Okay, we have to present all 4 records in the feed forward flow, and you have to get the hidden layer output. So I just to show the process, I'm doing it manually, one after another. Say for example, okay, let me do it from here in this cell. Can you see here I'm supplying 4 data points. 0, 1, 1, 0, 1, 1, and also 0, 0. Maybe I'll take one more cell here. To supply 0, 0. Sorry, 0, 0. What is the target? 0. Rest other cells. I don't want this. Don't want this. I don't want this. Okay. Okay. At this stage, we have got this result, and this is the trained matrix is after training. This is the 3 by 3 matrix, which is updated after the satisfactory level of results, whatever we have got this result. Now, what I'm going to do, I'm presenting one after another records. One by one, I'm going to present the record. First, I'm presenting the first sample, 0, 0, target 0. What should I do? I should apply the dot product between the first record with the trained weight matrix to get the net value, and then I should apply activation function. This is the hidden layer output. Okay, this is hidden layer output. When I present the second pattern, this is the hidden layer output. Third pattern, this is the hidden layer output. For the fourth pattern, I got the hidden layer output. Okay. Now, I'm going to save this value. Okay. Because every time when I experiment, my weights will change accordingly. That value I used to take. But here, while I'm demonstrating you, I have got some different weights. I wanted to update these values. Let me copy. Okay, instead of copy paste, you can, in programming, you just refer the variable and you can, this manual process also, you can reduce it. But really, I wanted to show you what is happening. Let me manually copy paste this to represent. These are the transformed value of the 4 records, isn't it? H1, H2, H3. I just overwrite. Now I'm going to name this as a hidden neurons. So maybe I name this as a 1 to indicate it is a single layer, right? So it's a hidden neuron. So 0.555 is the output for 0, 0, right? 0.555. When you supply this 38.125, this third record after transformation, fourth record after transformation. This hidden neurons 1, okay, I'm going to prepare in the form of a data frame. Then only I can use Plotly 3D package. To use that package, you have to pass the data frame format and you have to specify what is the x-axis I should use, y-axis. So I have to properly define this, right? This transformed value in a form of a data frame by giving the name for it. H1, H2, H3, right? 3 axis. So that is what I'm doing here. Maybe you can parallelly you can prepare your input data along with the constant input, right, for the bias. So maybe the y-axis you can keep it like a bias variable. Probably, okay, you can try to represent your raw feature also in a 3 dimension. For that purpose, what I do, I prepare the input feature also in a form of a data frame structure. For that, I prepare this 0, 0 with it. This is x1, this is x2, this is the bias input. Okay. Similarly, 0, 1, 1, 0 along with the bias input. So the third column is 1 to indicate the bias input, so that I can try to show the input feature also in the third dimension. So your transformed values is prepared in the form of a data frame called HN. Similarly, my input feature also prepared in the form of a input feature data frame. This is the raw input, and this is the transformed in the hidden layer. So we have attached the labels also, right? X1, X2, and this is the input to the bias. To refer the input to the bias, I call this as X suffix B. And I wanted to color code because we are going to plot 4 records. These 4 records, 2 records belongs to one class, another 2 record belongs to another class, isn't it? So I need to color code it according to the label. So the target label also I'm attaching to the input as well as the transformed records. So in the input data frame, I'm attaching the label. The first record and fourth record belongs to class 0. Second record and third record belongs to class 1. And similarly to HN data frame also, we are attaching the labels 0, 1, 1, 0, right? We attach the labels. Now I'm going to call the plotly 3D plot. You can import plotly express as px. It's just a one-liner function, scatter underscore 3D. You have to pass the data frame and you have to specify what is the x-axis, y-axis, and the z-axis, what you want to have. So let me take this. So original features already we have seen in the two-dimensional graph. The data is not separable. In the 2D feature space, your original data points I will show the three-dimensional representation of the raw feature. But before that, we have known that 0, 0, 1, 1, these two data points belongs to one class. One, 0, 0, 1, where belong to label 1. This also label 1. This guy is label 0. This guy also label 0. Okay, with the linear boundary, we could not separate this, right? The raw representation. Of course, if you try to map this in the elevated representation also, in a three-dimensional representation also, I'm going to show you, still it's not separable. But however, the transformed representation, we try to comprehend this 3D graph. So how to comprehend this 3D graph? So in this, the beauty of this plotly 3D Express is interactive. So using mouse cursor, okay, you can able to rotate in any orientation. Also, you can zoom, okay, zoom in and zoom out. So which orientation you wanted to visualize, the respective orientation you can see. Just imagine this is like your room, right? Your three-dimensional view of your room. Okay, let me keep in this orientation. It looks better. So this vertical axis is H1, H2, and this dimension. So 3 axes are visible now, three-dimensional view. Can you see in the corner of the room, these 2 data points sits in one corner, and this another portions, these 2 data points belongs to another class. They are easily separable, isn't it? So your data points are easily separable. Whereas your original feature, okay, original feature, it is in x1, x2, and in the z-axis is bias. That means all your data points are taken to the elevation level 1, constant elevation level 1. Because the z-axis you have taken the bias input, which is one constant. That means your elevation level is a constant for all. That means imagine your 4 data points are floating somewhere in the air from the floor level with a fixed distance. Assume it's a 1 meter distance from the floor, because your z-axis is one constant for all 4 records. Initially at the floor level, your data points are in the diagonally. Okay, the diagonally 2 records belongs to one class. Opposite diagonal, the 2 records belongs to another class. And project it in elevated level after 1 meter elevation, assuming the z-axis is just like a 1 meter elevation. Still, you could visualize the data points were not separable in the original feature space. So you have to see, can you see from the floor level, these 4 guys are elevated. They have got elevated with a fixed height, 1 meter. Because your XB score is 1, constant value 1. Can you see these two are at the opposite diagonal and the red data points are the opposite diagonal? So your linear model find it very impossible to separate these guys. You're able to visualize why they are not linearly separable in the raw dimension, original feature space. They're not separable in the original feature space. Wherever you draw the boundary, they're not separable. But in the transformed feature space, they are separable. So you just play around with this 3D Plotly 3D Express and try to see, because your iteration numbers are different. Okay, your initializations are different. Remove the seed value, random seed value, and try to see the transformed values are separated, beautifully separated in the transformation phase. Like this kind of a visualization, okay, I would take you to another interesting visualization. So in the presentation slide, I have provided the link for that visualization, Professor Karpathy's JavaScript visualization. So you copy paste that link. So this is slide number 17, Stanford link. In case if you are also working parallelly with me, try to open that link in a different browser. I'll tell you how you have to run that simulation. See, this is the screen. So what you have seen is the layer by layer design. In fact, let me explain this layer definition. Even though it is being written using a JavaScript, we are going to use the TensorFlow framework shortly. Okay, don't mind the this coding part of it. Anyhow, we are going to use a different framework, TensorFlow Keras framework. But the logic you can easily understand. More or less, your TensorFlow framework also, which includes the components, whatever the components it involves. Can you see it specifies the first hidden layer? It is going to use 6 neurons. 1, 2, 3, 4, 5, 6. In our code, we have transformed the 2 inputs to 3 neurons, right? Here they are transforming to 6 neurons. And second, one more hidden layer, which comprises of 2 neurons. Okay. And this is the last output layer, which is one hot encoded, 2 neurons. And your input is 2 variable, like 2 features, x1 and x2. This is the architecture. So unlike our code uses 1 hidden layer architecture, but this is a 2 hidden layer architecture. So what we have used sigmoidal activation function, but here what activation function is used is a hyperbolic tangent activation function. So at every stage, it will get the range value -1 to +1 instead of 0 to 1. That is the only difference. But remember, in the output side, softmax is used. Softmax is the scaled representation of the sigmoid. So output is a probability score. So I should have the value between 0 to 1. Okay, 0 to 1. But anyhow, you can alternatively you can use the sigmoid also in the output. Only when we extend to more than 2 nodes multi-class, sigmoid softmax is mandatory. Okay, hold on, I will explain the softmax when I introduce the framework. Okay. So this is the architecture. So the beauty of this simulation is you can visualize the data points at every level, like hidden 1, hidden 2, till up to the last layer. You can visualize the data points. Okay. Let us start with a simple data. Okay, this data it's quite simple, but still they are not linearly separable, isn't it? Look at the original feature space. I may not maybe this is the best line I can draw. Still, there is a one record is being misclassified, right? Here, this yeah, I think only one record is being misclassified. So that is why this is called simplest of the pattern. Let us see what going on. At least one record is being misclassified, right? But when we use this architecture with the 2 hidden layer architecture, obviously all the records are successfully classified. So how to navigate, how to visualize layer by layer? If you click this FC6, that you could see how your input is visualized after transferring your input map onto the first hidden layer. You are visualizing the net value before applying the activation function. FC6 means you are mapping onto the hidden layer with the 6 neurons and before applying the activation function. After applying the activation function, your data points, you could see some green circles and red circles are going through certain transformations. Please make a note of it. Even though we have 6 neurons, the simulation is a 2D simulation, 2D graph. Please understand, 1, 2, 3, 4, 5, 6 neurons. It's impossible to visualize all 6 at a time because maximum human eye can see only 3 dimensions. But what is being taken here? Only the first 2 neuron output alone taken for the visualization, H1 and H2. And then we are mapping onto the second hidden layer after activation function. And finally, your output layer, you could see all the red data points are mapped. Okay, you can see this is something like a sigmoid function at the output. These 3 data points are lying closer to 100% probability. These data points are close to 0% probability. They are linearly separated. The data points are successfully, all the red data points and all the green data points are successfully separated. We have, in fact, we have a very big margin between the 2 classes. This is being a simple record. But little complex records, look at this kind of data points is a bit complex. Even in our TensorFlow playground, in the very first session, I have demonstrated TensorFlow playground. We required at least minimum 2 layers we required. Okay, let us try to see the data points, how it navigate stage by stage. First at FC6, still it's not separated, isn't it? After applying activation function, still red and green data points are mixed up a little bit, even after transforming the data point to the first hidden layer. Then mapping onto the second hidden layer, applying activation function. Overlap is reduced, isn't it? Overlap got reduced. That is the reason they may think that, okay, up to 2 hidden layer itself, transforming the data to 2-stage hidden layer itself, your data points are separated. And mapping onto the probability scale output, all the red data points and all the green data points are very well separated. Still, we have a very good margin. Bit complex. This looks very complicated. Even we have this pattern in our TensorFlow playground also. For the complex pattern, okay, it's almost separated, just with one mistake. I think there is only one mistake. This green record is being misclassified as red because they are in the red zone. With one or two mistakes, we were able to successfully do it. Okay, we'll see this step by step. After mapping onto the second hidden layer, after applying activation function, because of the complexity of the data points, okay, we were not able to maintain the large margin like the way we maintain the large margin for the other samples, right? So the margin is very thin, and still there is one misclassification. Maybe to by extending this architecture to one more layer, or by increasing the neuron in the second layer, maybe try to solve this. Okay, let me edit this to 3 neurons. Okay, I'm editing this code. You can able to edit this code, edit this and change network. I have changed the network with the 3 neurons. Okay, let me take the same spiral data again. Mapping onto this, I would like to see the final output. So it's not satisfactory. Maybe I increase this to maybe 5 neurons. Make it as a 5 neurons. I change the network. Still at the boundary, one green record is behind this red, I guess. Okay, it's overlap. That is why it's not visible to it. You could slightly see there is one green data point is behind this. Maybe the reason is they are overlap. Can you see the original pattern? Okay, original pattern. Both are having the same feature. Not possible, right? In the reality, you cannot say either you have to put it in one class or another class. If the features are same, okay, if x1 feature is this match, x1 feature is this much and x2 feature is this much. For the same combination of the features, you are trying to say they are same class. Maybe by increasing the feature, third feature, and maybe you can say that you can differentiate it. Okay, since it's an illustrative process, but in the real life problems, we have more features. Even if the two features are same, the third feature or the fourth feature will try to differentiate such overlapping data points. For example, age 36 and body mass index is 22. This age group person may be a healthy, same 36 with a BMI 22. Maybe the person may be a diabetic. Maybe if you consider some other characteristics, okay, some other characteristics like glucose level and exercise habit or eating habit, these features, if you consider, okay, even these two features are overlap, the other features try to give the component to differentiate the records. So just you can visualize what is happening through hidden layer. Okay, for that purpose, this visualization could be helpful. Okay, now I'm going to introduce the framework. Okay, so after understanding the mathematics, without any API, without any library, we have understood the concept. Now I take you to sklearn framework. So let us go to lab 3 notebook. Okay, lab 3 notebook. So till lunch, we'll see, I'll introduce one framework. Post lunch, I'll introduce the TensorFlow Keras framework. Okay. Also, I will tell you why sklearn framework is not so popular. So towards the first step, I'm going to use the multi-layer perceptron model, whatever we have designed to solve a linearly non-separable problem. Of course, that is a toy data. It's not a realistic data. Now we are going to see a realistic data set which has a nonlinearity issues. You may hear about this Boston dataset. It's one of the popular dataset. Over learning data science and machine learning, you never miss this dataset. It's one of the popular dataset, which comes from University of California, Irvine repository. Here, the intention of this dataset is to predict the house price. And why particularly I have taken this dataset is typically this dataset people try to use linear regressor to predict the price value. The last column of this dataset is what the price of the property is given in thousands of dollars. For example, the first record with all features, and they say 35.5. What is the interpretation? The interpretation is $35,500. First, you have to scale with $1,000. Second record, it says something like 22.8 means it is $22,800. So why the unit is very important is when you try to validate the performance, it is very particularly for the regressor problem. With unit only, you can validate the model performance, and accordingly, you have to fine tune the model parameters. So for regressor problem, your output variable unit is very, very important. Randomly, you cannot tune it. And moreover, even though theoretically you could have studied a different metric like R square, adjusted R square, then sum square error, mean square error, the most practical metric, mean absolute error, mean absolute percentage of error, the most practical metric for the regressor problem is, irrespective of whatever the model you choose, root mean square error. Because the root mean square error, you can able to express the model performance to the context of whatever the units I'm dealing with. Here, it's the price of the property. Suppose you are predicting the blood glucose. The blood glucose value is represented as milligrams per deciliter. Okay. For one record, actual is 100, but model predicts 120. Another record, the actual is 135, but model predicts 140. What is the difference? It's over predict with 20 milligrams. Okay. Here also, it over predicts with 5 milligrams. Some case it may under predict also. If actual is 140, if the model predicts 130, it under predicts with 10 milligrams. Whenever it under predicts, positive difference, over predicts negative difference, right? So your RMSE, it is a direct indication of the average difference. How we are updating this? Because we square it, we sum it, and we take the average. We square for our mathematical convenience. Okay, to remove the effect of the squaring, I have to apply the square root to get the RMSE score. So the RMSE score is basically implies what is the average difference. Sometimes it over predicts, sometimes it's under predict, but what is the average difference? So your RMSE score try to communicate the value, what is the average difference in units. So in that perspective, whoever used Boston data set, people who get introduced to data science and machine learning before they come across neural network, obviously they could have tried with different models, starting with the linear models, linear regressor. And then maybe they tried a KNN regressor, decision tree regressor, a random forest regressor, and so on. You know, the best score, the best RMSE score achieved without neural network architecture. So I have taken a linear model also just for a comparison. I will show you. So excluding the neural network architecture, when you try linear regressor model, your RMSE score will come somewhere around $5,800 plus or minus $1,000. This is a rough value. It varies according to how you design and what kind of features you use. Okay, what kind of data preparation you do. Slightly the value will change, but this is the best score you can achieve. Somewhere around the 5,500 to 5,800, or the worst case around $6,000. The average difference. Whatever the tuning you do, whatever the choice of feature selection you do, you never achieve something below $5,000, the average difference. So we are going to, because of its non-linear nature, obviously your linear model was not so effective. Of course, maybe you could have tried with KNN regressor or random forest regressor, decision tree regressor. They could able to get somewhere closer to $4,800. Okay, maybe the random forest may bring the score close to 4,000, maybe $4,500. So with the traditional nonlinear models, have marginally improvised the scores. Okay, marginally, but again, if this bias error is better, they have to compromise more on the variance error. That issues also will be there. So this plus or minus value, we call it as a variance error, the variability factor. Okay. So to judge the model performance, if you do the k-fold cross validation, right? Assume that you do three-fold validation. For every fold, when model will learn based on the two folds and do the prediction based on this fold, right? And gives y cap. And I'm comparing the actual value of this folder y. Based on this difference, I report one RMSE. Similarly, the next two folds are combined for the training model.fit, and this fold is used for the prediction. I calculate y cap. This y cap is compared with the actual y of this guy. I take a RMSE score. Finally, you combine these two guys, right? Combine these two guys and use this fold for prediction y cap and compare with this actual y. Based on this, you get another RMSE. These three RMSE, if I take the average of this, it directly indicates the bias error. And these three RMSE, if you calculate the standard deviation of these values, it indicates the variance error. That is how we are going to validate the performance. So towards the first step, I'm going to use sklearn module. In sklearn package, okay, we have something, the package name is called as MLP regressor. If you are solving a classifier problem, you can use MLP classifier. Okay, only for this session, I will be using this particular exercise. I will use sklearn library. Moving forward, the remaining till tomorrow, we'll be using only TensorFlow Keras. Let me comment these packages for time being. Okay, I will tell you the reason for this post lunch. Towards the first step, we are going to work only with sklearn package. Since I'm going to retrieve my data from the Google Drive, I have to mount my Google Drive. So mount the drive and then read. I'm reading this housing.csv file is being shared with you. So either you read from the local machine as a standalone Jupyter, or using a Colab, you are retrieving from the Google Drive. Make sure that you upload the data in the respective current working directory. So as I told you, the last column is the variable we are supposed to predict. Can you see the first record, $24,000? This is $24,000. $24,000. This is $21,600. $34,700. $33,400. $36,200. So if you have used linear regressor and other models, maybe make it as a homework task, or whenever you get a time, you just try to apply this model and try to see the score. But definitely you will not get even around $5,000 as the average difference. Maybe if you try to get even below 5,000, maybe around $4,800. But definitely I'm damn sure you will reducing it below $4,500 with any other nonlinear model. You may not bring this, only with the help of neural network. You know, the neural network is going to give us a very stunning result. We were able to bring the bias error close to $3,500. No other model has touched the score around $3,000. So the average difference of $3,500. And also the variance error somewhere close to $500. So this kind of result is possible only with the help of a nonlinear models. On a selected configurations, please understand. Okay, anybody having the built-in library cannot achieve this score. You should be able to tune it with the properly experimentations and with the selected configurations. Whereas your sklearn will not provide you enough scope to tune it. Layer by layer tuning scope will not provide. Okay, we are going to see how sklearn library. In sklearn library, you can only tell, hey, you use 3 layers, you use 2 layers, and each layer use these many neurons. That's all. But layer by layer, you can define what activation function. Just like this demo, this code demo we have seen, right? The layer by layer, you can see one layer tire H, another layer you can use sigmoid, another layer again. So you can experiment, because at one stage of the transformations, maybe your hyperbolic tangent will give a good separation. Maybe another layer, maybe you have to explore with the sigmoid or another activation function. So this layer by layer design control, your TensorFlow Keras framework will provide. Whereas here in the sklearn, you have to define the whole model with only one variable. That's all. So before that, let me define X and Y. My input is this. We scale the record. For post-lunch, I will show you the importance of why I have included Keras here. This is mainly for the TensorFlow modeling. Okay, I'm importing MLP regressor. Here I'm using MLP regressor. So this is what the model definition. Can you see? Using MLP regressor. Here using SK, okay, there's only one parameter called hidden layer sizes. Hidden layer sizes. So you have to represent in parentheses. I have used the number 70, 100, 70, then 80. It's not how I arrived this number. It's not it's not magic. It's just pure experimentation. Okay, to start with, always is a good practice to start with one layer. Okay, to start with one layer. So I remove. So how many inputs we have? Around 13 features, right? Yeah, 13 features. The thumb rule is, okay, if you start with one hidden layer, the thumb rule is you try to define the neurons. Okay, you try to define the neurons either 2 times of your input or 1.5 times of the input to start with a simple neuron. Okay, 13. Maybe I'll start with the 25 neurons, nearly 2 times. 25 neurons with one hidden layer. Okay, I wanted to see the performance. So my ANN model is defined. And then I'm going to validate the performance, right? To validate the performance, I require, see, your simple train test split will not give the judgment about the bias error and variance error. That is the reason we go for cross-val score. Because if you go with the simple train test split, the entire records you divide, okay, this is the train and this is the test, this is the validation data. You cannot judge, say for example, okay, for this training record, your model give around say $4,800 RMSE score. And for the test record, it gives like $5,000. Assume that you take the result to your client and your client will say that, okay, for the training record, $4,800 and for the validation record, $5,000. Your client may give another set of records. Can you tell me for this bunch of records, your model will be performing close to 4,800 or close to 5,000? We don't have an answer for it, right? So that is the reason we go with the k-fold cross validation. When you go with the k-fold cross validations, you will have a range estimate. This is a point estimate. So we perform k-fold cross validation. So for that, I import this library. I have given a loop for time being. I'm not running this loop. Okay. The reason here is because usually the learners will ask me, sir, like unlike other sklearn models, can we apply grid search CV? Unfortunately, your grid search CV will not accept, okay, will not accept the hyperparameter of hidden layer sizes hyperparameter because it's a multi-dimensional, multi-layer hyperparameter. Whereas your grid search CV, which is available in your scikit-learn package, it can do the grid search for a single dimensional hyperparameter. Say, for example, when you do it for a KNN model, you have to tune the n neighbor value. Okay, n neighbor value, you can define a range. Okay, you can say somewhere around 3 to 30, and also with some, you give other argument, for example, weights equivalent to distance. So by default, it will do unweighted distance. So by setting the weight component, you can say so weighted distance or unweighted distance. Assume that a model you use two hyperparameter. Okay, one hyperparameter is like a string. Okay, say string val1, or so maybe it's option 1, option 2. Maybe, okay, I'll consider a distance metric, maybe the another way. It's a Euclidean distance. Another one may be Manhattan distance. This is variable 1. Variable 2, which is a numeric. You need to search 3, 5, odd numbered value you want to search. Because so that for the even numbers to avoid the tie, particularly if you're using for the classification problem, for regressor, no issues. Let us assume like 3, 5, 7, 9, 15. Assume that I'm tuning it for classification problem. What your grid search is going to do, for Euclidean distance with 3 neighbor, it is going to do one model. Model.fit, model.predict. It is going to do threefold cross validation according to the fold size you specify. In grid search CV, you have to specify the fold size. With Euclidean distance, it will try with five neighbor combination, 7 neighbor with Euclidean distance, like 1, 2, 3, 4, 5. Okay, another 5 combination with Manhattan distance. Totally 10 models. It will try to do validation, model.fit, model.predict, based on number of fold validation you specify. It's a time consuming process. First of all, it's a time consuming process. It is going to take too much of time. In fact, if you are going to give a This is a discrete range. If you're going to give a sequential range also, it's going to take too much of time. So that is not the criteria, that is not the limitation for the grid search CV. Here, the nature of the hyperparameter is like either a discrete form, or you can give range, right? np.a range, you can specify 3 to 20. Between 3 to 20, it is up to 19, it is going to check. But in our hyperparameter, it is a multi-dimensional variable. It's not going to have, if it is like a, okay, for one hidden layer, if you wanted to check the different neuron variations, if the hyperparameter is like that, you can do it, because this is one variable. You are trying to change from 3 to 30 or 3 to 20, you check. But it is not a one variable, it's a multi-dimensional, it's a multi-layer. So first of all, if you try to use a grid search inside the grid search CV, if you try to pass MLP classifier, first of all, it's going to throw an error. It will never accept MLP classifier, or sorry, here MLP regressor or a classifier inside the grid search CV. But on top of it, is there any alternative equivalent to grid search CV, so that manually we don't want to experiment? Imagine you are saying that, sir, manually I don't want to experiment. Let me give it to the something equivalent to grid search CV. Is any solution is there? Yes, there is an option called customized grid search. You have an option customized grid search, but this is not recommended because it's a too time consuming process. Just for two layer itself, just for two layers itself with 1 to 60 combination, start with one neuron up to 59 upper limit, one neuron up to 1 to 59. What it is going to do, assume it's hidden layer 1, hidden layer 2. It's going to work with one layer combination, one with the two combination, one, or if like this, two neuron, one layer, three neuron with the two neuron combination, four neuron with one combination, four neuron with two combinations. Likewise, your hidden layer 1, it is going to experiment between 1 to 59. Similarly, hidden layer. So how many combinations it has to try? 1 with 1, 2 with 1, 3 with 1, it goes on, 59 with 1. Then again 2 with 1, 2 with 2 with 2, 2 with 2, 3 with 2, goes on, 59 with 2. Again 3 with 1 with 3. Sorry, here I missed 1 comma 2. 1 with 3, 2 comma 3, and so on, 59 comma 3. So all the combinations, the model will try to create an architecture, and it's going to perform cross-well score inside it, and it's calculating the mean and standard deviations. So you have to wait for simple architecture is okay, but little bigger architecture, even sometimes you have to wait for hours. But rather using the grid search, maybe just out of a curiosity, if you wanted to run and see, just you run and see how much time it takes. Okay, but what is highly recommended is the logical way of tuning the architecture. So the logical way, what is the logical way? We know it. Initially, to start with a one layer, if your data is not converging, it's not minimizing the loss, gradually I have to increase the neurons in that layer. Even after increasing the neurons in that layer, still your model is not able to reduce the loss function. Then you have to introduce another layer and gradually increase the neuron. That is the logic. So there is no there is a standard formula to tell that how many neurons are required in each and every layer. It is purely experimental. So I start with one layer with 25 neurons. Okay, I'm going for a k-fold cross validation here. Okay, I'm not running this because it will take too much of time. If you are curious, you can run this cell in your notebook and see how much time it takes. Since here I'm tuning two layer, okay, two hidden layer. So nested for loop, I index and j index I have used. In case if you wanted to tune the third layer, okay, you have to introduce another nested loop for k varies from np.a range. You have to try with minimum one neuron, say up to 100 neurons if you wanted to try. So the third dimension you have to specify. So every time model layer sizes ij, right? So the third dimension I should introduce here, ijk. First layer, second layer, third layer. So I'm not introducing here. The whole code I have to intend, but I don't want to intend this. So currently let it be like a 2-layer tuning, because the 2-layer tuning itself, it is a time consuming process. Okay. So what we do, we perform simple cross-well score for the ANN reg model. This is the ANN reg model we have defined with one hidden layer architecture. You know how to operate cross-well score, your model, X and Y, the scaled X. So there are two styles. Either you can directly specify CV value here, or you can randomize it using k-fold function. So the benefit is it is going additionally is going to shuffle the records, and also you can set a random state. The reason is because every time if you run it, any changes in the architecture if you do, it's very difficult for you to judge, because every time if you run this, what happens now? The splits, the number of records allotted for each fold will be different. And if you do some slight modification in the architecture and when you see the result, it's very difficult for you to comprehend whether the change in the result is because of change in the architecture or because of the changes of the samples I have selected for the folds. So it's very difficult to comprehend, right? So for that reason, so the explicit definition of k-fold is recommended. Otherwise, you can directly pass the value also. Okay, let me do 5-fold cross-validation for RMSE score for this design. Look at the huge error. I told you even the linear regressor model gives a score of $5,800. Look at the score, it gives $9,800, very high bias error. Even with one hidden layer architecture is underperforming than a linear model. That means a wrong choice of neurons, number of neurons. So it's not at all sufficient. So what I do, I try to increase this neuron maybe to 50 neurons. I just double the neurons to see whether always your first focus should be on the bias error. Then you come to the variance error. So that is a standard tuning, not only for the neural network, generally for any machine learning model. The logic here is, I just give a simple analogy to understand why you have to give a focus to the bias error, then you get a satisfactory bias error, then you get a focus on the variance error. The simple analogy is, you just think a cricket player. Okay. So as a coach, imagine you are a coach. You want to see the performance of a particular player. Maybe during an IPL season, you are monitoring the performance. First of all, you want to see a person, whether it's a batsman, let us consider a batsman. What is the objective for the batsman? To get a good score, right? You want to see that, okay, your target is you prepare that batsman to give at least 30 to 40 runs. Okay, so this is what your target. Your particular player, you are going to train it, and that based on this performance, you have to select for the Indian team for the next season. Assume, okay, in IPL season there will be experiment. There are so many teams will be there, so many Indian players, right? Across all the teams, you may get across 50 players, but when you go for a season like ODI, okay, your 11 plus substitution alone will go. Okay, so as a coach, you wanted to monitor a particular player. You focus on the scores individually first. Okay, your target. Okay, why the player is struggling to get scores? You want to get the focus on getting a score, a decent score. Once earlier, the player used to get 5 to 10 runs, right? You slightly improvise to 20 runs at least. At one point of time, the player started giving a 40 to 50 run. This is what you expected. Yeah, okay, it's giving 40 to 50 runs. Then you come, but the problem with that player is One match he scores 40, but another match he scored 5 runs, 50 runs. There is no consistency. Then you try to work on the consistency. What is the issue? Sometimes you work, sometimes it's working for you, sometimes not working for you because of the pitch or because of a different bowler you are not performing. What is the reason? You should be able to provide consistent performance irrespective of the pitch condition or irrespective of the bowler. You should be able to give a consistent score somewhere around 40 to 50. So first, my aim is to bring that player to a decent number. Then you try to bring the consistency. First of all, if the player is not enough prepared to bring a decent number, what is the goal of bringing the consistency? That is the reason whenever you tune the architecture, first I'm not focusing on my variance error. Okay, first I wanted to get a decent score. What is a decent score? Getting close to $5,000. Getting close to $5,000. So earlier it was $9,800. The moment I increase the neuron, can you notice from $9,800, your RMSE score has reduced to $7,500. That means a good improvement. At one point of time, however you increase the number of neurons in the hidden layer 1, you may not achieve a better score beyond a particular point. That is the point you have to introduce another hidden layer. That is the strategy. Okay. Now let us see. Okay, from 50 neurons, I'm going to increase to maybe 80 neurons. So it should be in the multiples of 10. Why not 86? Fine. I'll choose a number something like 86. $7,500. Can you see improvement? Again, bias error. That means your loss is reducing. Your bias error is indication of your loss. Your loss is reducing it from $7,500. It reduced to $6,400. Very good improvement. Make it as 100. $6,400. $6,000. Can you see the difference is minimized? Earlier from 9.8 suddenly 7.5. Some 7.5 suddenly the difference is a very big jump. But from 6.4 it's a marginal change. That means your hidden layer 1 is almost getting saturating. That's an indication. Okay, from $6,400 to $6,000. Fine. By another, let me try to add another 15 neurons. $6,000, it's getting saturating one more time. See, it's oscillating. See, it reaches the minimum, again it's increasing. It's almost your $6,000 is a saturation point. It's keep oscillating, right? So that is the freezing point. You have to consider somewhere close to 100 is the ideal point. Your layer 1 gets saturated. Now you introduce the layer 2. Keep on increasing the neuron in layer 1 will not help. Now I introduce another 50 neurons. I have to start with another 50 neurons in the second hidden layer. And I wanted to validate the performance. What was the best score so far we have got? $6,000, right? Approximately. See the big difference. The big difference, the moment I introduce the second hidden layer, the big difference from $6,000 to $4,580. Again, by increasing the neuron in this layer, at one point of time, it gets saturated. Say, for example, at maybe I try with 70. It should not increase the score. Anything below the score, it's a promising. Anything above the score, it's not recommending. That's the meaning. So getting oscillating. Maybe I'll check with 65 neurons. So far, 4,500, right? Is the best. $4,500. Yeah, $4,350. So around 60, 65 is a saturation point. If I touch a 70, again it's oscillate. So by second layer, I fix 65. Then if further reduction, if anything below $4,300 is possible or not, then I try to introduce the third layer, maybe with 50 neuron to start with. 50 neuron. Good sign, right? So it is meaningful to introduce a third hidden layer from $4,350, but of course the margin $4,200. So further increasing the neurons in this layer is going to be helpful or not. I'm going to check. $4,200 is the so far the best. Oscillating. Okay. So I may finally check one more combination somewhere between 50 to 60. I try 55 neurons. So let us fix 50 itself. 50 itself. So this is what, once you got a satisfactory result of the bias error, then you can check, play with the variance error. Okay, for this combination, what is the best variance error you are getting? So this is the best architecture possible with sklearn library MLP around $4,500, close to $4,500. Maybe adding another further layer whether it's going to improve the performance or not. The fourth hidden layer, let me introduce, and I'm going to check the bias error. So your model got saturated at maximum at 3 levels. So within the 3 levels, you have to play around with other steps, right? Now you decided, okay, you have to play around with these 3 layers in terms of activation function, layer wise activation function. Here the default is the sigma del activation function. The problem here with MLP regressor is once whatever the parameter you choose, that is common for all of the 3 layers. That is the problem. But on the other hand, layer by layer design is possible with the TensorFlow Keras framework. Look at this. Here is the layer by layer design. Post lunch, I will discuss about this. For example, one layer, if you wanted to use tan H, you can use another layer if you wanted to use sigma del. Okay, and this kind of a customization is there. So obviously, your TensorFlow Keras based design will be more flexible than your sklearn design. So post lunch, I will try to show you how you can modify any other activation function with this within this MLP regressor. And so whatever the changes you do, maximum you cannot reach the best score beyond the 4,300. So far, the best we have got around $4,300, isn't it? Around $4,300. So to freeze the record, right? Because every time you changes in the architecture, right? Your model takes a different set of training and validation record because your fold samples will vary. So for that, I have to freeze the records, right? For that, if you explicitly define this, so whatever the changes in the architecture you do, okay, I have frozen the records. The same validation record and the same training records will be used for the 5 folds. Then you are able to make a good judgment. Okay. So here I fix a particular random state, for example, with the random state, it's with a fixed random state. If any changes or any tuning you do in the architecture. So with now I have shuffled the records. After shuffling the record, okay, with the same architecture, I perform. So I'm getting $3,854. $3,854. Now you can see with the same set of training and validation record, by increasing the neuron from 55 to 60 is going to be helpful or not. $3,854. 3,500. So it gets settled somewhere around 3,500. You may not go below this score, right? But it is a very drastic improvement when compared to linear models. See, I told you linear model cannot achieve something below $4,800. And other nonlinear models like a KNN regressor, decision tree, random forest can touch up to $4,000. Only neural network model can able to bring the score below $4,000. Not only that, you will able to get a decent variance error score also. But however, with MLP, with sklearn library, we are getting the score. Okay, post lunch, I will show you with more control over the parameters. Even we can reduce the variance error to what level is to $660. Look at this, the best score achieved so far, $3,340 with plus or minus $660. Bias error also improved as well as the variance error also improved whenever I move from sklearn library to TensorFlow library. But still, post lunch, we'll try to use some other parameters and we'll try to see is there any other better improvement is possible from this. Okay. So at this moment, let me stop